Hi, and welcome to 8.7b Conservation of Energy 2. In this lesson, students will be able to apply the law of conservation of energy to different situations to calculate unknown physical quantities. Just more practice with the law of conservation of energy in different situations. Like this one, a pendulum. Now, pendulums are going to come up again in Unit 13 when we talk about simple harmonic motion. But for now, we can talk about the energy in a pendulum. A simple pendulum consists of a mass, which is called a bob, which is hung by a string from a fixed support. It hangs vertically in its equilibrium position. So right now it's going back and forth. It's oscillating about its equilibrium position here. But if it wasn't moving, it would just hang straight down, obviously. When the bob is displaced from equilibrium and then released, it begins a back and forth motion about its fixed equilibrium position. So in the classroom, I like to hang a big bowling ball from the ceiling in a big pendulum, and then I swing it back and forth, and it's a classic physics demonstration. I am going to put some videos in the extension folder of some other, dare I say, even better physics teachers than me doing that demonstration. They do a really good job of doing that. So that's in the extension folder if you want to check it out. But we can still talk about this on the slide. So where would you say the highest kinetic energy is? And where would you say the highest potential energy is? At which of these positions? Pause the video and give me your answer. Hopefully you can see at position 3, that's where the bob is moving the fastest. And actually that little vector that's going back and forth, that arrow, is the largest. You see how it's the largest? That vector is the velocity vector. So you're moving the fastest as you go through the equilibrium position, and then you slow down to a stop for a split second at the very top before you turn around. So when you're turning around, you stop for a split second. That means your kinetic energy is the lowest over here. Okay, so where would your so the highest kinetic energy is here. So we'll make like a boom, KE. Where is the highest potential energy? Pause the video and think about it. Well, if you were going to measure from here as your base point, all right, this is the lowest you could get. You could even measure from the ground still, but let's say our 0 points here. The highest point is over here. So this is going to be your highest gravitational potential energy on this side. And then yes, if you said over here, that's also very true. So this is where you have the most GPE. And the cool thing about pendulums is it can exist in between those 2 points too. So you have a combination in between over here. I highlighted the maximum, right? So over here, you have no GPE here, but it's maximum KE. And over here, we said you're not moving, so no KE, maximum GPE. But at this position right here, you have some height above that level, right? So you do have some GPE, not as much as over here, and you are moving, but you're not moving as fast as you would be over here. So you do have some kinetic energy, but not as much. But the combination of your little GPE plus your little KE is going to give you the same amount of energy at all points when you add both of those together at all points along the path. So that's the general gist of why pendulums are cool to talk about with energy. We could ask a couple more questions like, where is it losing kinetic energy? So answer that question. So hopefully you said when it's slowing down, it's losing kinetic energy. When it's like going this way, I wish I could pause it. Maybe I'll write over here. So if it's on its way up over here, then it's losing KE. And when it's on its way up over here, then it's losing kinetic energy over there. That's kind of just a cool way to think about it, I guess. All right, so where is it gaining kinetic energy? Where is it gaining kinetic energy? Think about that. As it's on its way towards equilibrium, it's getting faster. If it's like at position 1 and going this way. And then it swings back, and now you're at here. And then as it's swinging towards equilibrium again, you get gaining kinetic energy. How about losing potential energy? Hopefully this one's easier to think about, right? If you're losing potential energy, what happens? Pause it. If you're losing potential energy, that means you're losing your height. So that means, again, kind of the same as the previous one where you're going towards equilibrium. That means you're losing the potential energy. And if you are up here and you're going towards the equilibrium position, you're losing potential, you're gaining kinetic, that type of thing. Where is it gaining potential energy? When it's gone past the equilibrium position and is going up, that's when it's gaining potential energy. So that's cool. There's a couple other questions. Why does the system lose energy? So when I do this in the classroom, I have this slide up and it says, why does the system lose energy? Because it doesn't go back and forth forever like this one is. Eventually it stops. So stop the video and give me your answer. The system loses energy because it gets transferred into internal energy or heat over here. Plus, you do have some air resistance, depending on how big that bob is. You'll have some air resistance associated with that. So that will take energy out of the system in the form of internal energy or heat. It's not going to be super hot, but it is like vibrating those particles, and that's where the energy goes. How can we add energy to the system? So if I was standing over here and I was going to release, so the whole idea is I have this big pendulum and I release it from rest right near where my face is. All right. And then I'm confident that it's not going to hit my face because it can't gain energy. It's not going to get to a higher position unless I do something. How can we add energy to the system? If I push on the ball, if I push on the bob, I exert a force over a distance, then I can do some work on the bob. And by doing work on the bob, I'm adding energy to the system. So not only do I have this gravitational potential energy, I'm adding in, so GPE, the total energy is going to be the potential energy plus whatever work I do by doing the force. I'm just pushing on it, force times distance. And then I got to be careful because if I do that, it's going to come back to a higher position because it'll be all that energy. So it's initially you have the work plus the GPI initial, and then the height over here, it's going to get to a taller height because you have these two together giving you a higher final potential energy. All the energy goes somewhere. You just have to figure out where. So that's kind of cool. All right, so this is another GIF of the energy of a pendulum. You could rewatch this as many times as you want. I've spent hours watching this because it's fascinating to me. So you could see where it's the highest kinetic energy and the highest potential energy. Here's another GIF of a roller coaster. And the total energy of the system dissipates. You saw that little sound wave and the crunching of the metal takes that mechanical energy out of the system because it's really like non-conservative forces at that point. So that's pretty cool. All right, here's another demonstration I do in the classroom. Typically, it says a ball is released from the top of a ramp. How high does the ball go as it rolls up the other side? So if the whole thing is like, ooh, it's got a long time to accelerate over here. Well, I'll pause the video and let you think about it. So here are some schools of thought. It's got a long time to accelerate. So does that mean it's going to get fast? And then it doesn't have as much of a distance to decelerate. Like this is a longer distance. This is a shorter distance. So does that mean it's going to go flying off the top of the ramp? That's one school of thought. The other school of thought is to get that to happen, then you release it from here because this is a steep angle, right? So it's a steep angle. It's going to go fast, and then it's going to go to the other side. But actually, it's a gravitational potential energy problem where if you don't push it, you just release it from rest. If you don't give it some initial velocity, if you don't give it some initial kinetic energy, it's all GPE here, all right, then it's going to be all GPE on this side. And what happens is it looks like this. Comes up right to the top, and then it goes back and forth, back and forth. It does eventually stop. Why does it come to a stop? Because there's friction, internal energy. So we could do an example with a pendulum. It says a pendulum is made from a 2 kilogram mass attached to a rope. The mass is pushed to the side until it's at position A, 3 meters higher than its equilibrium position. So that's shown over here. They're telling you the vertical distance up, all right, coming over here. What is the total amount of kinetic energy that the mass has as it swings freely through the equilibrium position? So what is the kinetic energy at this point? And what is the maximum velocity that the bob reaches? And hopefully we know. Where would that occur? The velocity occurs, the maximum velocity occurs right in the middle, like we said before. It's moving fastest through the equilibrium position, and it slows down and gains kinetic potential energy over here. All right, so let's try that out. Or if you want, you could pause the video and try it out for yourself. So the mass is 2 kilograms. We are on Earth. Don't want to get points off for not writing units because we can see we're going to do some kind of potential energy thing here. All right, the height is 3 meters. All right, and then we're looking for the kinetic energy. All right, so I mean, you could do the potential energy first, and that'll tell you the amount of joules of energy that that bob has. It has 58.8 joules of energy at this position right here. And all of that energy gets transferred to kinetic energy at this point. So what you could do is just write your kinetic energy formula. So you could do KE, oh my gosh, freaking out a little bit here. Okay, there we go. KE is equal to 1/2 mv squared. And then the idea is if you're comfortable with the law of conservation of energy and you know that all of this energy is purely transferred into kinetic energy, you could just plug it in as kinetic energy at that point. That's typically kind of what I'll do. But I'm going to show it a different way. So I'll finish this. Oh, actually, we just answered part A, right? It says, what is the kinetic energy? And then to do part B, you plug in the numbers. And 1/2 of 2 is 1, so you end up just taking the square root of 58.8, and you get 7.7 meters per second, 7.668, whatever. All right. That's one way to do it. If you know, like, all of the energy is being transferred from one to the other. The precise way to do it would be to use that formula we used in the previous lesson. So you know that the total energy at one point is going to be equal to the total energy at another point. So you pick your 2 points. All right. Point 1 is going to be over here. This is like the initial condition. And then over here is going to be the final condition because we know that's where the equilibrium position is, and we know where that's where the maximum velocity is going to be. So and then you ask yourself, you do the checks. All right, what type of energy? Because I'm not going to write out the whole formula like I did before. What type of energy is present in the initial situation? Are you moving? No. At that point, you don't have a velocity because the bob is turning around and it's released from rest. All right, so you're not moving, so there's no kinetic energy. Are you a height above a 0 position? Yes, you are. You're a height above that, the minimum distance that you could get there. So it's 3. So you have a height there. So you do have GPE. So I would write GPE initial. The next check is, are you compressing or stretching a spring? No, you are not compressing or stretching a spring, so there's no elastic potential energy. Then you could even ask, is there friction? It doesn't say anything about friction here, so let's ignore it, okay? So we got that. That's equal to, at the final position, are you moving? Yes, you're moving through the equilibrium position, so you do have some kinetic energy. And I'm going to do KEF because there was no initial kinetic energy, but we do have a final kinetic energy between those 2 points. Are you a height above a 0 position? No, you are at the minimum distance that you can get. You're not going to get lower than that. Are you compressing or stretching a spring? No. Is there any type of internal energy? No. So that is kind of how you could do that. You just do the checks and you make your life a little bit easier. Now we could do mgh, the initial height is equal to 1/2 mv squared, the final velocity, because the initial velocity was 0 and the final height is 0. So that's what you're going to do. Then we're going to plug in the numbers. And actually, I keep on forgetting that A is just purely asking for the kinetic energy. So if you wanted to, you could write it like this. You keep that kinetic energy term just the way it is, and then that'll tell you the answer to the problem that you get 58.8 joules. That's going to be equal to your kinetic energy. So that's pretty sweet. That's the answer to question A using our nice, this is a nice thorough way to look at things, right? The total energy stays the same. Then you could do what is the maximum velocity that the bob reaches. You can plug in your numbers the way we were going to. So that's 1/2 2 times VF squared. So 1/2 of 2 is 1. So then you get VF squared again, and you take the square root, and you get the same thing. Just a different way to do it. VF is equal to 7.7, we said, when you round it, meters per second. If you get super comfortable doing these things, you could just set the energy equal to the other, the first method that I did. But when you get more complicated problems, like if the bob is in the middle and you have multiple types of energy on one side of the equation, this is, I think, the better way to go about doing it. So it's good practice. When it's simple like this, it's good practice to do it this way. All right, so we're gonna one more question, and I hardly ever like pull out the New York State standards and just throw them in your face like this, but for when we're talking about energy, it's kind of useful to look at. So it says for 4.1e, it says in an ideal mechanical system, the sum of the macroscopic kinetic and potential energies, the mechanical energy, is constant. In an ideal system, the mechanical energy is constant. In a non-ideal mechanical system, as mechanical energy decreases, so that means for some reason the kinetic and or potential energy will decrease, there is a corresponding increase in other energies such as internal energy. So if you are losing mechanical energy, it's because of most likely friction, some kind of internal energy. So you can lose mechanical energy, but that doesn't mean you lose energy overall. The mechanical energy gets transferred into non-mechanical energy or like internal energy, like friction. When work is done on a system, there is a change in the total energy of the system. Just like when we were holding the bob, I was holding the bowling ball pendulum. I was holding it at a certain GPE, and I could do work on the system. I could push it, and I'm actually adding energy to the system. I could also do negative work on the system. We talked about negative work, and I could take energy out of the system. So by doing work on a system, we can change the total energy. Work done against friction results in an increase in the internal energy of the system. So this is kind of saying the same thing of before, where if there's friction involved, there's going to be internal energy. So here's an example that shows that. This is straight from the Regents. It says, as represented in the diagram, a ski area rope tow pulls a 72-kilogram skier from the bottom to the top of a 40-meter high hill. The rope tow exerts a force of a magnitude 158 newtons to move the skier a total distance of 230 meters up the side of the hill at a constant speed. So the rope is pulling this way with a force of 158 newtons, and the displacement is in the same direction. See how they labeled that in the diagram for you? The rope and they're trying to show that the displacement is parallel to the force. So if you think about the work being done, it says, A, determine the total work done by the rope on the skier. We're not actually going to have to do any kind of sine or cosine because it looks like, ooh, I could figure out what the angle is. And Mr. Nangle said, oh, WD cosine theta. That's only when, I mean, that's there, but the angle would be 0 degrees. All right, because the angle between the force and the displacement is 0. They're parallel to each other. So yes, there is an angle here, but they're wording the problem so that you can do a pretty easy calculation for part A. So let's do that. Okay, so I'm going to write in that thing again. And let's write our given information. And watch this. The distance that you go up the hill is 230 meters, but the height that you gain along that trip is 40 meters. So I'm labeling them differently, distance and height. All right, this is your height. So the work done is W is equal to the force times the distance. These two, right? The 230 and the 158. So the work done, 158 times 230. We are doing 36,340 joules of work. So you might expect, okay, I'm doing that much work. And that means I must be gaining that much potential energy. Maybe my GPE at the top is going to be 36,340 joules. Part B says, so this was A, Part B says, calculate the total amount of gravitational potential energy gained by the skier while moving up the hill. Well, the GPE is equal to mgh, the height, and this is equal to 72 kilograms times 9.8. Oh, I'm writing 9.8 and I forgot to write it over here. So I'm just going to come back and write it over here. That's fine. Times 40, because that's the height that you gained. And you get, look at that, it's different. The GPE is only 28,224 joules. We did more work than the energy, the gravitational potential energy that we gained. I wonder what happened to that other energy. What happened to it? Describe what happens to the internal energy of the skier hill system as the skier is pulled up the hill. The correct answer for this is that the internal energy increases. And here's why. If we do the same thing before, this is like our initial condition, and at the top, this is like the final condition. The total energy in the beginning, it has to be equal to the total energy at the end. Maybe not the mechanical energy, but we have that other term, Q, for internal energy. So let's see what that looks like. Right now, I'm not moving. I don't have any height. All right. So right now uh, actually, this is a tricky way to look at it because we are doing work on the system. So there's this outside force doing work on the system. So the work done is equal to the potential energy that you gain, the GPE at the end, plus the internal energy, Q. All right. So yeah, it's going to increase as you go up the hill. You gain potential energy and you gain this internal energy. And it says describe, and we could calculate it. So if you wanted to, the work that you do, we said was 36,340. And we calculated your final potential energy was 28,224. And we want to know how much internal energy is that. It's just the remainder. So Q in this case would be equal to 8,116 joules of internal energy. So it says describe what happens to the total mechanical energy of the hill system as the skier is pulled up the hill. The mechanical energy consists of your GPE, or sorry, the mechanical energy is just potential energy in general and your kinetic energy in general. So ignoring the fact that, yes, there is some internal energy. All right. Some of that work that you're doing is being transferred into internal energy, which is not mechanical. But, so that is true. But what happens to the total mechanical energy of the system? That's kind of like where we ran into trouble over here. In the beginning of the situation here, you didn't have a height and you didn't have a velocity. Then you start moving. So let's say you're moving with a constant velocity. So you have a constant kinetic energy, and your gravitational potential energy increases. So you have an increasing GPE because you're going up. So since mechanical energy consists of potential and kinetic, and we know that the potential energy is increasing because we're gaining height, we can say that the mechanical energy also increases. All right, because you're doing work on the system. Very nice. All right, that's about it. Thanks for watching and have a great day.